First, let us take a look at the most commonly used information criteria and the logic behind them. The general formulae for Akaika information criteria and Schwartz information criteria are shown here. These two are often used for model selection, and these formulae are adjusted slightly for the selection of lags in VAR and VECM. These information criteria work by imposing penalties on including more variables in the models. This means that any additional variables or lags in the model must contribute to a better fit, otherwise, they will have a poor impact on information criteria. The lower the value of AIC or SIC, the better the fit of the model. If an extra variable or lag in the model leads to a higher value of AIC or SIC, then we can consider that variable unnecessary. This leads to a situation where we choose a model that has the lowest value of information criteria. In case of VAR and VECM, we have to slightly adjust the general formulae. We estimate the value of information criteria at different lag lengths. For instance, we can calculate the AIC and SIC at lags 1, 2, 3, 4 and 5, and choose the lag which has the lowest value. If a model with 3 lags has the lowest value for AIC or SIC, then we can estimate a VAR with 3 lags. For VECM, we use 1 less lag than its VAR formulation, which would mean 2 lags in the VECM model. Software programs like R and Stata make it easy to implement this procedure of lag length selection using information criteria. In R, you can use the command varselect provided by the vars package. Stata provides a similar inbuilt command varsoc for estimating information criteria at different lag lengths of VAR models. It is important to note here that these commands are tailored for VAR models. Suppose the results of these commands indicate an appropriate lag length of 2 lags. Then, we can use 2 lags of variables in the VAR model. However, it is different in the case of VECM. We can say that these commands indicate the number of lags for the underlying VAR model. Therefore, we have to use 1 less lag in the VECM formulation. For instance, if the commands indicate a lag length of 2, we have to specify 1 lag of differences in the VECM. This brings us to another important point, that we must be careful when specifying the lags in software programs. Some programs ask to specify lags for the underlying VAR model, while others might ask to specify the lags of differences directly for a VECM. For example, when estimating a VECM model, Stata asks for lags of the underlying VAR model. On the other hand, the VECM command in our package called tsdyn asks for the lags of VECM directly. Finally, even the information criteria is not a foolproof system for choosing lags. It is possible that the VECM or VAR model might still suffer from autocorrelation. That is why it is essential to apply certain goodness of fit measures to be sure that the model is a good fit. Suppose you observe some residual autocorrelation after estimating a VECM, which makes the results unreliable. Then, you will have to increase the number of lags in the model. This means that you have to include more lags than indicated by the information criteria. You can increase the number of lags till the problem of autocorrelation is eliminated. When it comes to constants and trends, we usually have the option to choose from 5 different types of specifications in VECM. These 5 types of specifications are unrestricted trend, restricted trend, unrestricted constant, restricted constant, and no trend and constant. Here, we will discuss all of these one by one. First, let us take a look at the unrestricted trend specification. The equation here shows the matrix form of VECM with an unrestricted trend. What this means is that the VECM includes a constant and linear trend in the first differences, which is the short-run part of the model. Moreover, we also have a constant and a trend in the cointegrating equation or cointegrating vector, which is the long-run part of the model. Therefore, we can say that there are no restrictions applied to constants or trends in this model. This is why we call it the unrestricted trend specification. We use this specification when the variables show a quadratic trend in their original form and the cointegrating equation is trend stationary. This makes sense because if we have a quadratic trend in levels, we will see a linear trend in the first differences. As a result, we need to include a trend and constant in the first differences. This specification also allows the cointegrating vector to be trend stationary because we include a trend and a constant there. Next, we have the restricted trend specification. This includes a constant and a trend in the cointegrating vector similar to the previous specification. However, we include only a constant in the first differences and the trend coefficient is removed from the VECM. This means that the cointegrating equation or long-run equilibrium can still be trend stationary like before. We use this specification when we see a linear trend in levels or the original form of variables. This means that we only need a constant after taking the first differences in the VECM. Like before, the cointegrating vector and long-run equilibrium relationship will have a significant trend and we allow it to be trend stationary in this specification. In the unrestricted constant specification, we include only constants and remove the trends from the equation. That is, we have a constant in the first differences and a constant in the cointegrating vector. This means that we have a linear trend in level variables and the cointegrating equation is stationary around a constant mean. There is no trend component in the first differences or in the long-run equilibrium relationship. We use this specification when the original variables have a linear trend, therefore, we need a constant in the first difference form. Also, the long-run equilibrium or cointegrating equation does not have a significant trend and it is stationary around some non-zero mean. The restricted constant specification includes a constant only in the cointegrating vector. Hence, we do not include a constant or a trend in the first differences. This implies that the level variables are stationary around a constant mean and there are no trends. In the cointegrating or long-run relationship, we allow the relationship to be stationary around a constant mean without any trends. We use this specification when the variables do not show any trends in their original form and they seem to revolve around a constant mean. As a result, we don't need any constant or trend after taking the first difference. In the case of the cointegrating vector, this specification permits a stationary long-run relationship around a constant mean without any trend. Finally, we have the no trends or constants specification, which is the most restrictive specification for a VECM. This type of model is rarely used in practice because it does not include any constants or trends. That is, we do not include a constant or a trend in the first differences or short-run part of the model. And, we do not include a constant or a trend in the cointegrating vector. This specification makes sense only when the level variables revolve around a constant mean and the cointegrating equation is stationary around a zero mean. It does not allow trend in original variables, and no non-zero means in their first differences or the cointegrating equation. Thank you for watching and I will see you in the next tutorial.